Greetings. I have one block diagram left to show you, and it's the power distribution block diagram, essentially how the power is sent to the various blocks on the remote system and the current consumption. Now, where does it start? It starts at plus 48 volts. Yes, 48 volts. Why? To keep the currents going up the tower into small wires as low as possible. With 50 volts, which is pretty much the output at the power supply that I have, 2 amps will be plenty of current to drive a DC-DC converter, and that converter is more than 90% efficient. This is it. Okay, it's a small cube. It's what we call a half brick size DC-DC converter. It's a C&D Technologies model VKA 150 MS12. It's a 12 volt DC-DC converter. It can take from 36 volts to 75 volts in, and it produces 12 volts out, and it can be trimmed down to 10 volts. That's the nice thing about it. So I will trim it down to plus 10, plus 10.1, plus 10.2, maybe to compensate for internal losses in the box, but around 10 volts, and it's good up to 150 watts. So no problem delivering up to 10 amps at 10 volts, as long as there is some heat sinking on that unit though. This has to be bolted down to a plate, and of course with some thermal interface to increase power dissipation. So that is what I'm going to use here. So roughly 8.5 amps at 10 volts in transmit mode. So I will fuse that 10 volts. 10 amps is a little too close for comfort. I will probably use a 12 amp fuse if I can find one. So how does it distribute to the system? The 10 volts goes straight into the MDR 8010 GHz power amplifier. That's in transmit. In receive it draws nothing. Okay, so only in transmit, 6.7 amps constant, whether you send RF into the amp or not. It's a Class A amplifier. Yep, big power hog. Now this 10 volts is also sent to our remote controller board with the Raspberry Pi Pico. And of course, on this board, what do? We sequence the plus 8 volt transmit and receive. We also send that same 8 volts from the LDO regulator to the synthesizer and tripler to produce our LO signal. We have a plus 5 volt regulator to feed our onboard circuits, including the Raspberry Pi Pico, and that plus 5 is also sent to the OCXO, to the 10 megahertz ovenized oscillator. It's a 5 volt unit. At power up, for about 1 minute, it draws 700 milliamps, but it lasts around 1 minute. Maybe if it's minus 20 outdoors, it's gonna take 2 or 3 minutes. But during that time, it's probably best not to transmit anyway, because you are drifting. Now, in steady state, it draws around 250 amps on that 5 volt bus. Another 10 volt consumer is the coaxial antenna relay. I use a 24 volt relay, so I had to add a boost regulator that produces 20 volts, which is enough to switch that relay. So I send 10 in, it produces 20 out. It's a small little board. I use the same thing in the previous system. And on 10 volts, it will draw 240 milliamps, but that's only in transmit. I've also added, as you know, provision for a cooling fan, and I have a solid state switch, and I allocated 200 milliamps at 10 volts for the fan. So if we summarize the current consumption with no fan running, in the first minute after power up, when we're in receive, of course we won't be transmitting because the system is warming up, it'll be drifting like crazy anyway. The 10 volt current will be 1.46 amps, and after that warm up period of about 1 minute, the current will drop to around 810 milliamps at 10 volts. When we switch to transmit, it will be 8.4 amps. And of course, the bulk of that current goes into the 10 gigahertz power amplifier. So these are the currents we're dealing with. Imagine if I had decided to send the 10 volt supply up the tower on around 60 feet of cabling. We will have had a significant voltage drop on the line. And the best thing to do was to regulate up on the tower and send a much higher voltage, which allows to reduce the current to a maximum of 2 amps, which 20 gauge wires can easily carry up the tower. And even if there's some voltage drop here, I do not care. This guy can run from 36 volts to 75 volts. So I will still put out our 10 volts up on the tower regardless of the voltage drop on the power supply uplink. So that, I think, is the best solution. And the efficiency of this guy at 10 volts with 48 volts is 90+%. So yes, it will dissipate some heat, but I think it's a better solution anyway. Now, heat management will be the big thing here. I still haven't figured out exactly how I'm going to do it. I am starting to work on the enclosure, so I will come up with a way to cool down. It's not impossible that if it's very intense transmit receive for several minutes, that I may have to pause a couple of minutes to let the temperature go down a bit. You know, the enclosure will be relatively small compared to the power dissipated. And put that in the summer under blazing sun, it will make things worse, obviously. So we'll see how I deal with the heat. But as far as the currents go, very manageable. All right, that's what I wanted to cover today. See you soon in the next video. 7-3.